Ladies and gentlemen, Robert Teixidó.
Thanks for the introduction. My name is Robert Teixidó, and I'm here to talk about Tractivus, the company which I am CTO of. Tractivus provides solutions to implantable medical device. When you implant a medical device, such as a urinary catheter or a tracheal stent, there is a lot of problems due to its implantation. We have bacterial colonization, the migration of the device along the implantation zone, bleeding, necrosis, and the apparition of granulotic tissue. All these drawbacks force the extirpation or the removal of the implanted stent. All these drawbacks can be focused in two blocks: to treat the infection and to avoid the migration of the device. In Tractivus, we provide solutions for a specific implantable medical device, the tracheal stent. Tracheal stent is a cylindrical tube that keeps the airway opened. It's especially important in the case of the tracheal stenosis, a disease that causes a narrowing in the trachea walls, blocking the airway and provoking respiratory problems. It required the implantation of this stent to keep the airway opened, provoking such these drawbacks: 90% of colonizations, 11% of stent extraction, 12% of granulotic tissue, migration, and pain. The doctors call a new stent should be able to avoid the bacterial colonization and avoid the migration. In this context, Tractivus proposed two solutions. The first one, the development of a bioactive coating in the tracheal stents that is able to eliminate to reduce 90% the bacterial colonization, and the technology which I'm here to fabricate a completely personalized tracheal stent. Tractivus has a technology to, using the images of a computer tumorization scan, can design a 3D model of the patient's trachea and manufacture a medical silicon-based 3D stent. To do that, we use the DCOM images using a process from data extraction that identifies the trachea in the medical image. With this image, we have a methodology to, using the threshold of the gray scales, identify where are the trachea walls, and then extract this data. With this data, we create the 3D trachea model of the patient. We have a process for optimize these trachea models, correct the generated mesh, eliminating the conventional problems in this kind of process. Improve the resolution, reduce the plane orientation, the overlapped triangles, and the triangle intersection, obtaining a high-resolution trachea model of the patient. With this trachea model, we're able to isolate the region of interest on the trachea, and with help from a medical team, we can make the adequate modifications to try to obtain a personalized, completely anatomical stent that avoids the migration. The result is a stent which is completely adapted to the patient's trachea, reducing completely the migration of this kind of dispositives. When we have the 3D model of the stent, we print it using a 3D printing process to finally obtain a medical silicon-based stent with the anatomical geometries present in the trachea. You can see them in the expositor next to this table. Due to our expertise in tracheal modeling, we took part in a project with the Hospital Universitario de Sevilla, Reina Sofía, to provide or support in a pediatric tracheomalacia case. The pediatric tracheobronchomalacia is a condition that occurs when the walls of the trachea are weak and cause a collapse of the airway. In this case, the main bronchus is immature due to a problem in the growth of the patient and cause a collapsing, avoiding the correct function of the lung. Complications derived from the tracheobronchomalacia are the respiratory problems, pulmonary infections, sputum retentions, cough, and, in several cases, the death. In this particular case, was a severe case of tracheobronchomalacia and was a 5-month-old girl patient which has the right bronchus completely collapsed, clogging the airways and provoking a lung malfunction. The only way to keep the patient breathing was removing all day in the hospital the sputum directly from the lung. The medical team has planned an intervention for the complete extirpation of the lung and avoid this malfunction. The other treatment, still experimental in bibliography, consisted in the development of a splint for the collapsed bronchus that keeps the bronchus opened using stitches. This kind of device required a biocompatible material, a material rigid enough to keep the airway opened, and also biodegradable in order to eliminate all the material when the patient grows. So, with this case, we used the medical images from the patient to obtain a tracheal 3D model of the disease, observing where the malacia was placed. In order to scale, the lung of the bronchus was 22 millimeters. So we are talking about a difference in 1 millimeter in the open of the bronchus. The splint designed by us was a customized bronchus splint that keeps the airway opened and was perfectly adapted to the bronchus of the patient, with enough numbers of holes in order that the surgeon can make his stitches. We also fabricated, using classic stereolithography, a scale medical model in order to evaluate if the designed device completely fits in the 3D. And with this design, we make a collaboration with the Michigan University, with Dr. Hollister, in order to print the device in polycaprolactone by laser sintering. Polycaprolactone fulfills the required properties for this device in biodegradability, rigidity, and stability terms. Once the device was synthesized, it was fabricated, the surgical team made the intervention, which placed the device in the outside of the bronchus, fixing it with sutures. The intervention went successfully, and now the patient come back to home and has a normal life. So in the costs defined in this presentation, what are the new challenges for the 3D printing market? I will talk about the health market. Health market in 3D printing represents the 15% of the 3D printing market. It includes the implants, the chirurgical guides, and the instruments. And if you want to make something in this market, we think that events like that are important, but also we need more certificated and adequate printers to perform health applications. Printers that are completely isolated in a white room and able to print devices like that, devices like can be implanted directly for the surgeon. We also need, of our point of view of implanted 3D printing devices, a new range of certificate medical materials. We printed this scaffold in polycarbonate because fulfill the properties and it's FDA approved. But we also need more materials to unlock a new set of applications in the health field. And also, we need a clarification of the medical regulation in what's the role of 3D printing, the implantable 3D printing devices in the market. Without of that, it's really difficult to keep doing things like that. And, well, I want to thank the rest of the Tractivus team for this job performance. I want to thank Joan Gilabert, the CEO of the company, and Salvador Borrós, Victor Ramos. And thank you for your attention.